Here we're going to talk about what's called the sampling distribution of the proportion. So the sampling distribution is a very special normal distribution. We've seen several examples of normal distributions. Many things that occur naturally follow roughly a normal distribution, like heights of people or weights of loaves of bread coming off an assembly line. Now we're going to look at a special example. We're focusing our attention on one population proportion, on the case when we're interested in the proportion of a large population that falls into some category. So the proportion of voters planning to vote for a candidate, or the proportion of all consumers who've heard of your product, or the proportion of all smokers who eventually develop lung cancer. And the symbol we use to talk about that population proportion that we're interested in is lowercase p. Now we can't usually measure p directly because the population is too large. We can't actually survey everybody in the country and see how many of them smoke. Instead, we look at samples from that population and look at the proportion in the sample who fall into the category. So when we do that, the size of our sample is usually denoted n, and the sample proportion is denoted p with that little symbol on top, and it's pronounced p hat. So p is for the whole population proportion that we can't actually measure, and p hat is our sample proportion that we get by sampling a relatively small part of the population. So the cool thing is that the collection of all the possible sample proportions, all the p hats that you could possibly get for a fixed sample size, it's huge. Think how many samples of size 1,000 people there are out of this country. This is called the sampling distribution of the proportion, and the important parts, the mean of all those huge numbers is the actual population proportion. That ought to make sense. If you sample 1,000 people and say how many of them smoke, sometimes the proportion you get will be less than the actual proportion for the whole country, and sometimes it'll be more. And you kind of expect it to balance out, and this just says that it does. It has standard deviation, square root of p times 1 minus p over n. That's very surprising that there is such a formula. And it follows a normal distribution, especially for large n. In the hundreds is fine. So the sample proportions, when you go out and sample a bunch of individuals from the population and look at the proportion that fit into your category, that sample proportion is itself one number from a huge normal distribution. So let's see how this works in practice. So suppose we know that about 18% of all US adults smoke cigarettes. In a random sample of 1,000 adults, how likely is it that less than 16% smoke? Now, in all samples of 1,000 adults, you'll get different proportions. Some will be more than 18%, some will be less than 18%, some of them will be close to 16%, some of them will be less than 16%. But the mean of all those sample proportions is 0.18, the same as the population proportion. And the standard deviation, well, we have our formula. Standard deviation is square root of p, 1 minus p over n, or in this case 0.0121. So now we have a normal distribution with mean 0.18, standard deviation 0.0121, and we want to know how likely is it that we get one particular sample proportion that's less than 0.16. So now we just have a normal distribution problem. We find the z-score that goes with 0.16, that's negative 1.265. We use norm s dist and get 0.05, so there's 0.05 of 5% is less than that, and so that's our answer, 5%. So if the actual population of adult smokers is 18%, if 18% of the adults smoke, then the chances of finding only 16% or less in a sample is about 5%. Let's look at another example. Suppose an election is tied. Each candidate is getting 50% of the vote. How likely is it that in a sample of 1,200 voters, a pollster will find 630 or more voting for her candidate? Well, we're assuming that p equals 0.5, the race is tied. Our sample is 1,200, our sample size rather is 1,200, and the sample proportion, well, 630 out of 1,200 is 0.525. And the standard deviation, again by assumption that the p equals 0.5, is 0.0144. So now we have a normal distribution with mean 0.5, standard deviation 0.0144, and we want to know what's the probability that one individual is more than 0.525. If we take one sample, how likely is it that our sample proportion is more than 0.525? We find the z-score. Normalized dist is 0.96. But we asked about more than 630, so this is one of those cases where we need to subtract from 1 or from 100%. We got an answer of 4%. If the race is tied, there's only a 4% chance you would find 630 or more voters voting for your candidate in a sample of 1,200 voters. And so I hope you can see that if you just did find 630 or more out of 1,200, it would make you pretty sure that you were winning. So that's a brief introduction to the sampling distribution of the proportion.